this video, we're gonna continue our discussion on dynamic modeling for our processes. We're gonna start off by looking at some preliminary mathematics that is going to be necessary for this course. In this video, we're gonna start our discussion by comparing the models that we get for steady state versus unsteady state. For steady state models, we've been writing steady state models for our mass and energy balance classes, and we get algebraic equations. Linear algebraic equations, non-linear algebraic equations, we have an abundant set of tools to tackle them and get solutions either analytically or numerically. For unsteady state models, you'll have differential equations. And this, as you can hopefully see, occurs because of the change with respect to time terms of our variables. For the most part in this course, we'll be dealing with ordinary differential equations. And hopefully I will show you some examples of partial differential equation models and the techniques we can use to tackle them. But ODEs are gonna be the meat of this course. Okay, let's look at a first order model for a dynamic system. Let's suppose we have our output variable y and our input variable x. The following equation captures a first order dynamic relationship between our input x and the output y. You'll notice two parameters that I've highlighted here. K is what known as the gain of the process. We will get to a more formal definition of the gain later, and tau is the time constant of the process. And these are the two parameters you'll need to know to fully characterize a first order dynamic model. So in order to demonstrate the significance of the gain and the time constant, I'll show you how changes in x affect the changes in our output variable y. So let's say our value of x is at an initial steady state, and at time equals some t naught, the behavior of x is represented by a step function. So initially at a steady state value, and then it jumps up to a new steady state value. This type of behavior can be captured by a step function. And this step function represents the turning on or turning off of a switch. So in this case, it is turning on a switch. We are going from a low value to a high value in this case. So let's see how y is gonna behave for a first order model. So y is also at its initial steady state up till the time the step function is turned on. Now y would also start increasing if you have a positive relationship between x and y, but the change in y is not going to be instantaneous, rather it's going to take some time for x to catch up with the change in x. And hold on, let me make this a bit more cleaner. Okay, that looks a bit better. So y also goes from an initial steady state and it tries to reach a new steady state, as you can see here. Now the total change in y will be equal to the gain k multiplied by x, and this is where the definition of gain comes into play. So for a step response, the gain of the process is defined as the total change in output over the total change in input for a step response. And this definition is valid for first order models, it's valid for second order models, it's valid for any higher order model. Okay, so now we have a precise definition for k. Let's focus on tau for a minute. Alright, you have t naught here, and at t naught plus tau, what we're gonna observe is that, let me make some room here. At t naught plus tau, the value of y is gonna reach 0.632 times the total change in y. Okay, where does this definition come from? Like, why 0.632? That seems like an awfully precise number. So if you were to analytically solve this differential equation for a step response, in x, the solution to this differential equation is going to be y of t equals k times it's going to be the initial y at, we're going to call that y at t below t0, so that was our initial value of y, plus k times the change in x. So we have the step, we know how much the value of x has changed, and this multiplied by 1 minus e raised to power t over tau negative. So when you plug in t equals tau here, notice what happens. We have y of t equals y t less the initial value of y plus k delta x 1 minus e raised to power negative 1, because you're gonna have tau over tau. Okay, and this number turns out to be 0.632 rounded to 3 decimal places. And this equation, you'll see, comes out to be y at t equals tau is equal to initial value of y plus 0.632 times the total change in y. I'll use the definition of the gain to replace k times delta x by delta y. Alright, so that's where the definition of tau comes from. I'll write it here. Tau is the time taken to reach 63.2% of the total change. And this definition is only valid for first order systems, only valid if you have a first order system. It does not hold the same meaning for higher order systems. So notice how if you have two graphs, one for x and one for y, and the behavior of x is represented by a step function, the graph for the respective behavior of y has been given to you, you can easily calculate k by dividing the total change in y by total change in x, and you can look up the value of tau by figuring out how much y is gonna change at 0.632 of the total change and read that respective time. Keep in mind that this time interval, not this absolute time, this time interval between the time of step and the time at which you're reading, this time interval is gonna be tau. Alright. So that completes our discussion on a first order model that is captured by two parameters, k being the gain of the process and tau being the time constant. The gain of the process tells you how sensitive our output variable y is to our input variable x, and the time constant tells you how fast or slow the process is. In upcoming videos, we're gonna look at higher order models, and we'll also look at non-linear models. For most chemical engineering applications, we have multiple first order models in series, and when you have first order models in series, like let's say a battery of CSTRs, for example, and the equations that capture the behavior in each CSTR are first order models, then the relationship of X, which is the feedstock to the first CSTR, and Y, which is the product stream from the last CSTR. This relationship is actually going to be higher order because we have multiple first order models in series. And most chemical processes are also nonlinear. Most chemical processes are nonlinear. We'll find, like, as we start writing mass balances and energy balances, we'll encounter multiple terms that introduce nonlinearity into our equations. Our kinetics are not going to be very linear. We're going to have source and sink terms, etc. However, we'll try to deal with these problems by linearizing our models. So that's just a preview of where we're headed. And hopefully this video was helpful for you, and we'll continue our discussion of models in the next videos.